Deep learning, a subfield of machine learning, has revolutionized the field of artificial intelligence. It allows computers to learn from vast amounts of data, enabling them to perform complex tasks previously thought impossible for machines. At its core, deep learning leverages artificial neural networks, inspired by the structure and function of the human brain, to model complex patterns and relationships within data. This approach has led to breakthroughs in various domains, including image recognition, natural language processing, and robotics. The ability of deep learning models to automatically learn features from raw data sets them apart from traditional machine learning methods. Traditional machine learning often requires manual feature engineering, a time-consuming and expertise-dependent process. Deep learning, however, automates this feature extraction, allowing the model to learn the most relevant features directly from the data. This automated feature learning is particularly powerful in image classification, where complex visual patterns can be difficult for humans to explicitly define. The ability to process vast data sets and automatically learn intricate features makes deep learning a highly effective approach for image classification tasks. From identifying objects in photographs to diagnosing medical images, deep learning is transforming the way we interact with visual information. Deep learning models, specifically convolutional neural networks, or CNNs, have achieved state-of-the-art performance in image classification challenges. These models are capable of recognizing objects, faces, and scenes with remarkable accuracy, often surpassing human performance. The success of deep learning in image classification has fueled its adoption across various industries, including healthcare, automotive, and security. Furthermore, the availability of large image datasets and powerful computing resources has further accelerated the progress of deep learning in this domain. The increasing accessibility of deep learning frameworks and libraries such as TensorFlow and PyTorch has democratized the field, enabling more researchers and developers to build and deploy deep learning models. The open source nature of these tools fosters collaboration and innovation, leading to continuous advancements in deep learning techniques. The future of image classification and computer vision is deeply intertwined with the continued development and application of deep learning. As deep learning models become more sophisticated and computationally efficient, we can expect even more transformative applications in the years to come. Neural networks are the fundamental building blocks of deep learning models. They are composed of interconnected nodes organized in layers that process and transform information. Each node receives input from other nodes, performs a computation, and passes the result to the next layer. This layered structure allows the network to learn increasingly complex representations of the input data. The input layer receives the raw data, while the output layer produces the final prediction. Hidden layers located between the input and output layers perform the crucial task of feature extraction. These layers learn to identify patterns and relationships within the data, transforming the raw input into a more meaningful representation. The depth of a neural network, referring to the number of hidden layers, is a key factor in its ability to learn complex patterns. Deeper networks can capture more intricate relationships, but also require more data and computational resources to train effectively. Each connection between nodes has an associated weight, which determines the strength of the connection. These weights are adjusted during the training process, allowing the network to learn the optimal representation of the data. The learning process involves iteratively adjusting the weights to minimize the difference between the network's predictions and the actual target values. This iterative process is guided by a loss function, which quantifies the error in the network's predictions. The output of each node is determined by an activation function, which introduces non-linearity into the network. This non-linearity is crucial for the network to learn complex, non-linear relationships within the data. Without activation functions, the network would simply be a linear transformation of the input, limiting its ability to model complex patterns. The choice of activation function can significantly impact the performance of the network. Convolutional neural networks, or CNNs, are a specialized type of neural network specifically designed for processing grid-like data, such as images. They leverage the spatial structure of images to learn hierarchical representations of visual features. CNNs are particularly effective in image classification due to their ability to capture local patterns and spatial hierarchies. The core building block of a CNN is the convolutional layer. Convolutional layers employ learnable filters that slide across the input image, performing element-wise multiplications and summing the results. This operation, known as convolution, extracts local features from the image, such as edges, corners, and textures. Multiple filters are used in each convolutional layer, allowing the network to learn a diverse set of features. The output of each convolutional layer is a feature map, which represents the presence and strength of different features in the input image. Pooling layers are often interspersed between convolutional layers to reduce the spatial dimensions of the feature maps. This downsampling operation helps to reduce computational complexity and make the network more robust to variations in the input image. Common pooling operations include max pooling and average pooling. Max pooling selects the maximum value within a defined region, while average pooling computes the average value. After several convolutional and pooling layers, the extracted features are flattened and fed into a fully connected layer. This fully connected layer combines the learned features to make the final classification decision. The output of the fully connected layer is then passed through a softmax activation function, which converts the raw output into probabilities for each class. The class with the highest probability is then selected as the network's prediction. Activation functions introduce non-linearity into neural networks, enabling them to learn complex non-linear relationships within data. Without activation functions, the network would simply be a linear transformation of the input, limiting its expressive power. Various activation functions exist, each with its own characteristics and suitability for different tasks. The choice of activation function can significantly impact the network's performance. RealU, or Rectified Linear Unit, is a widely used activation function due to its simplicity and effectiveness. It outputs the input if positive and zero otherwise. RealU addresses the vanishing gradient problem, a common issue in deep networks where gradients become extremely small, hindering learning. Its computational efficiency also makes it a popular choice for large-scale deep learning models. Sigmoid is another commonly used activation function that maps the input to a value between 0 and 1. It is often used in the output layer for binary classification tasks. However, Sigmoid suffers from the vanishing gradient problem and can saturate for large input values, hindering learning. Its output is not zero-centered, which can also impact training. Softmax is an activation function typically used in the output layer for multi-class classification tasks. It converts the raw output of the network into probabilities for each class, ensuring that the probabilities sum to 1. Softmax is particularly useful for tasks where the input belongs to one of several mutually exclusive categories. Its output provides a probability distribution over the possible classes. Section 5. Loss functions, measuring performance. Loss functions play a crucial role in training deep learning models. They quantify the difference between the network's predictions and the true target values. The goal of training is to minimize the loss function, effectively reducing the error in the network's predictions. Different loss functions are suitable for different types of tasks, such as classification and regression. Categorical cross-entropy is a commonly used loss function for multi-class classification tasks. It measures the dissimilarity between the predicted probability distribution and the true distribution. It penalizes the network for incorrect predictions, encouraging it to learn the correct mapping between inputs and outputs. Minimizing categorical cross-entropy leads to improved classification accuracy. Binary cross-entropy is a specialized version of cross-entropy used for binary classification tasks. It measures the difference between the predicted probability and the true label 0 or 1. Like categorical cross-entropy, it penalizes incorrect predictions, guiding the network towards learning the correct classification boundary. Binary cross-entropy is widely used in various binary classification applications. Mean squared error, or MSE, is a common loss function for regression tasks, where the goal is to predict a continuous value. It calculates the average squared difference between the predicted values and the true values. MSE penalizes larger errors more heavily, encouraging the network to make accurate predictions across the entire range of target values. It is a smooth and differentiable function, making it suitable for gradient-based optimization methods. Section 6. Backpropagation, training the network. Backpropagation is the central algorithm used to train neural networks. It calculates the gradients of the loss function with respect to the network's weights, enabling the network to learn from its errors. The process involves propagating the error signal back through the network from the output layer to the input layer. During backpropagation, the gradients are calculated using the chain rule of calculus. The calculated gradients indicate the direction and magnitude of weight adjustments needed to reduce the loss function. By iteratively adjusting the weights based on the gradients, the network gradually improves its performance. The learning rate, a hyperparameter that controls the step size of weight updates, plays a crucial role in the training process. A small learning rate can lead to slow convergence, while a large learning rate can cause instability and prevent the network from converging. Backpropagation is computationally intensive, especially for deep networks with numerous layers and connections. However, modern hardware, such as GPUs, has significantly accelerated the training process, enabling the development of increasingly complex deep learning models. The efficiency of backpropagation has made it the standard algorithm for training neural networks. The success of backpropagation relies on the differentiability of the activation functions and loss function. The gradients can only be calculated if these functions are differentiable. This requirement has led to the development of various differentiable activation functions such as ReLU, sigmoid, and softmax. The choice of activation function can impact the effectiveness of backpropagation. Section 7. Optimization algorithms, fine-tuning the learning process. Optimization algorithms play a crucial role in training deep learning models. They determine how the network's weights are updated based on the calculated gradients. The choice of optimization algorithm can significantly impact the speed and stability of the training process. Different optimization algorithms have different strengths and weaknesses, making them suitable for various scenarios. Stochastic gradient descent, or SGD, is a simple yet widely used optimization algorithm. It updates the weights based on the gradient calculated from a small batch of training examples. SGD is computationally efficient and can escape local minima due to its stochastic nature. However, it can be sensitive to the learning rate and can exhibit oscillations during training. ADAM, which stands for Adaptive Moment Estimation, is a more sophisticated optimization algorithm that adapts the learning rate for each weight based on past gradients. It combines the benefits of momentum and RMSprop, two other popular optimization algorithms. ADAM is generally more stable and faster than SGD, requiring less manual tuning of the learning rate. It is often the default choice for many deep learning tasks. RMSprop, or root mean square propagation, is an optimization algorithm that addresses the vanishing gradient problem by dividing the learning rate by a running average of the magnitudes of recent gradients. This approach helps to prevent the gradients from becoming too small, allowing the network to learn more effectively. RMSprop is particularly useful for training deep networks with many layers. Momentum is an optimization algorithm that accelerates the training process by accumulating the gradients from previous iterations. This accumulated gradient, known as momentum, helps the optimizer to overcome local minima and converge faster. Momentum is often used in combination with SGD to improve its performance. Section 8. Building an image classifier with Python. Building an image classifier with Python involves several key steps. From data preparation to model training and evaluation, Python's rich ecosystem of deep learning libraries, such as TensorFlow and Keras, provides powerful tools for implementing image classification models. These libraries offer high-level abstractions that simplify the development process, making deep learning accessible to a wider audience. The first step is to prepare the image data. This involves loading the images, resizing them to a consistent size, and converting them into numerical arrays that can be processed by the neural network. Data augmentation techniques such as rotations, flips and crops can be applied to increase the diversity of the training data and improve the model's robustness. Next, a CNN architecture is defined. This involves specifying the layers of the network, including convolutional layers, pooling layers, and fully connected layers. The number of filters, kernel size, and stride are important hyperparameters that need to be carefully chosen. The choice of architecture depends on the complexity of the task and the available computational resources. Once the architecture is defined, the model is compiled by specifying the loss function, optimizer, and evaluation metrics. The loss function measures the error in the model's predictions, the optimizer updates the model's weights, and the evaluation metrics track the model's performance during training. Common evaluation metrics for image classification include accuracy, precision, and recall. The model is then trained on the prepared image data. This involves feeding the data in batches to the network and updating the weights based on the calculated gradients. The training process is iterative, with the model's performance gradually improving over time. The training progress can be monitored by tracking the loss and evaluation metrics on a validation set. Section 9. Real-world applications and examples. Deep learning-based image classification has found numerous applications across various industries, transforming the way we interact with visual information. From self-driving cars to medical diagnosis, deep learning is revolutionizing fields that rely on image analysis. The ability of deep learning models to accurately classify images has opened up new possibilities and improved existing processes. In healthcare, deep learning is used to analyze medical images such as X-rays, Connecticut scans, and MRI images to assist in diagnosis and treatment planning. Deep learning models can detect subtle patterns and anomalies that may be missed by human experts, leading to earlier and more accurate diagnoses. This can be particularly valuable in detecting cancers, identifying bone fractures, and analyzing retinal images. In the automotive industry, deep learning plays a crucial role in enabling self-driving cars. Deep learning models are used to identify objects in the environment, such as pedestrians, vehicles, and traffic lights, allowing the car to navigate safely. These models can also analyze road conditions and predict potential hazards, enhancing the safety and reliability of autonomous driving systems. In security and surveillance, deep learning is used for facial recognition, object detection, and activity recognition. Deep learning models can identify individuals in real time, track objects of interest, and detect suspicious activities. These capabilities have applications in law enforcement, security monitoring, and access control systems. In e-commerce, deep learning is used for product categorization, image search, and personalized recommendations. Deep learning models can analyze product images to automatically categorize them, enabling efficient search and retrieval. They can also be used to recommend similar products to customers based on their browsing history and preferences. Section 10. The future of deep learning in image classification. The future of deep learning in image classification is bright, with ongoing research and development, pushing the boundaries of what's possible. New architectures, training techniques, and applications are constantly emerging, promising even greater accuracy, efficiency, and impact. As computational resources become more powerful and data sets grow larger, deep learning models will continue to improve their ability to understand and interpret images. One promising area of research is the development of more efficient and lightweight deep learning models. This is particularly important for deploying deep learning models on resource-constrained devices such as mobile phones and embedded systems. Techniques like model compression and quantization can reduce the size and computational complexity of deep learning models without significantly sacrificing accuracy. Another area of focus is the development of explainable AI, or XAI, for image classification. XAI aims to make deep learning models more transparent and understandable by providing insights into their decision-making process. This is crucial for building trust in deep learning systems, especially in critical applications like healthcare and finance. The integration of deep learning with other technologies, such as augmented reality and virtual reality, is also an exciting avenue for future development. Deep learning can enable more immersive and interactive AR and VR experiences by providing real-time object recognition and scene understanding. This can have applications in gaming, education, and training. The development of more robust and adversarial-resistant deep learning models is also a key area of research. Adversarial attacks involve crafting subtle perturbations to input images that can fool deep learning models into making incorrect predictions. Developing models that are resistant to these attacks is crucial for ensuring the reliability and security of deep learning systems. Section 11, Conclusion, a new era of computer vision. Deep learning has ushered in a new era of computer vision, enabling machines to see and understand images in ways previously unimaginable. The ability of deep learning models to automatically learn complex visual features from raw image data has revolutionized image classification, impacting various fields from healthcare to security. As deep learning continues to evolve, we can expect even more transformative applications in the years to come. The development of convolutional neural networks, or CNNs, has been instrumental in the success of deep learning for image classification. CNN's ability to capture spatial hierarchies and local patterns makes them ideally suited for analyzing images. The availability of large image datasets and powerful computing resources has further fueled the advancements in deep learning-based image classification. Deep learning has not only improved the accuracy of image classification, but has also automated tasks that previously required significant human effort. This has led to increased efficiency and productivity in various industries. From automating medical diagnosis to enabling self-driving cars, deep learning is transforming the way we interact with the visual world. The future of deep learning in image classification is full of promise. Ongoing research and development in areas such as efficient model design, explainable AI, and adversarial robustness will further enhance the capabilities of deep learning models. As deep learning becomes more accessible and integrated with other technologies, its impact on image classification and computer vision will only continue to grow.